great to be here to give a colloquium. So as Quack mentioned, I've been on and off in Singapore since about 2009. So that was quite a long time ago, 9 years ago. And it's really nice seeing sort of the center here build up to what it is like today. So it's really a pleasure to come back and sort of give a talk about what really started as a piece of research here in CQT probably about 7 or 8 years ago, and it has evolved and really developed since then. So, and it's this idea of merging quantum mechanics with complexity science. So, as Quack mentioned, I'm now at primarily based at the School of Physical and Mathematical Sciences at Nanyang Technological University. So my group is distributed about the Complexity Institute there and the Center for Quantum Technologies here. So it's a highly non-local group. There's 3 group offices and no one knows where anyone is. So, and they don't know where I am either. But it works out fairly well. It's a LOCC mostly done. And what I want to highlight is really it's a nice, it sort of reflects the topic that I'll be talking about today, which is this interface between the complexity sciences and the quantum sciences. So it's this sort of this intersection here. And this, at first, seems to be a fairly peculiar intersection, because when we think about complexity science, people usually think about it in ties the dynamics of cities or sort of traffic networks, macroscopic systems. Whereas when we talk about quantum systems, we think about at the level of atoms, photons, and individual electrons. So these two sciences don't at first appear to be the most obvious ones that you'd want to intersect. But it turns out that there's a lot of parallels. And this is because complexity science, much like quantum mechanics, quantum information, started off to looking at sort of differential equations. They started off looking at nonlinear differential equations, chaotic behavior. But in the 80s and 90s, they started moving, like quantum physics, to use the language of information theory. People began looking at information propagation in complex networks, to look at how much information is being delivered from the past to the future. So they study a lot of the very similar topics, correlations, causality, and all using similar tools, the language of information theory. So when I started talking to the complexity theorists, there turned out to be a lot in common. And this is really a story about how we can take some of these concepts and join them together. Is it possible to dim the front lights, by the way, so that the screen's a bit... yeah, just play around with the control. Okay, great. All right, so what I want to tell you about is sort of this interesting interface and some of the nice results that we have today and some of the interesting possibilities in the future. So the starting motivation really comes from that of complexity, which in a lot of the studies that they look at, they tend to think about a system as a black box. They think about it as something that's very complicated, that we can't directly access internal dynamics. So it's kind of like the weather, the stock market. We don't really know how it works. And what we can see, observe, and see is a sequence of observations, sequences of data. And what they're very interested in is being able to build models of this data to understand how the past affects the future, to sort of models of causal discovery, so they can sort of postulate what pieces of the data here has effect on what we will see tomorrow. And the motivations, a lot of these models, is to be able to build them as efficiently as possible. And one of these measures is to be able to generate the right future predictions using as little information from the past as possible. So if two models were equally powerful, the one that used stored less information or needed less information about the past is often preferred. And there's two motivations to this. One is from the purely operational perspective. Storing information costs resources, collecting the data, storing it. It's generally energy intensive. And it's something that people want to avoid if possible. On the other hand, which is something that I want to emphasize more of, is that it also has a foundational component as well. And it kind of leads to this idea of improved understanding. The reason is really, when we think about what modeling is, it's when we think about sort of causal modeling or predictive modeling, it's really about capturing the information from the past that is of relevance to the future. And if we had no understanding about how a process behaves, then we don't know what elements of the past to throw away. So this, in the ancient days, with the cavemen, they looked at lightning bolts striking the sky, and they used that to predict whether they should go out for a hunt the next day. And the reason being, of course, they didn't really know what were the actual factors that caused sort of that sort of induce the likelihood of their preferred outcomes. And so they collected information, omens about just about everything. But as we get a better understanding about how the past affects the future, we can start throwing away information. So we can start getting rid of the unnecessary information, horoscopes and that sort of thing. We find that they're not that useful, so we can just throw them away. And in the end, we get a better understanding, keeping only the information that is needed, that is of relevance for future prediction. So as we get a better understanding of the causes of natural things, we can better isolate them, and we can gain better understanding. I think this is really this framework called Occam's razor, and has been echoed by scientists throughout the centuries. I mean, one of the first people, physicists who mentioned this was Isaac Newton, in his famous quote that we should attribute no more causes to natural things than both true and sufficient to explain their appearances. So the idea is really, we want to explain the most with the least. And we want to just throw away as much information as possible, and keeping only the information that is of relevance for the future. And I want to sort of illustrate this in a sort of fairly simple example, class of examples. And these are what's called stochastic processes. So they just correspond to systems where that emit are observed with discrete time steps. So you imagine that we're just looking at this object at each discrete time step t. We have the past from x0 to x past infinity, and the future from x1 to x positive infinity. And the idea of building a model is that we want to replicate this behavior. So the behavior of this process is described by this probability distribution between past and future. And we want to replicate it by taking information from the past, storing it inside some system in the present, so that systematic actions on the system at each time step will allow us to generate the correct future conditional statistics. So the idea is to be able to capture the correlations between the past and future in the present. And so this is really this frame of causal modeling. It was started in this field called computational mechanics back in the 80s. And since then, it's sort of it's built into sort of quite a systematic means of understanding just how the past affects the future. And the task is to find the system here that is, in a sense, minimal, the one that requires the least amount of information. So we can really isolate out the bits and pieces of the past that generates the right future statistics. So how do we go about this? There's always one particular way that always works. Just like the ancient cavemen, we can say that all the correlations are captured. I mean, all the correlations about this is contained somewhere in the past. So if we store the entirety of the past, that should be fine. And that's always a solution. We could always take everything we have observed in the past and dump it inside here. It's kind of like the caveman. We don't know what causes the future behavior, so let's just store everything. And you can see that that's probably not going to be very efficient. Take, for example, this being a completely random sequence, so just a completely random sequence of coin tosses. Then the amount of memory that's going to require to store all the past coin tosses is going to be unbounded if we look at this as a process happens ad infinitum. So that's obviously not the best way to go, since when we think about a sequence of random coin tosses, it doesn't really appear that complex. It shouldn't take an infinite amount of information to know what's going to happen in the future. The future is random anyway. So there's a more systematic way of taking out the relevant information. And this is basically the science of computational mechanics. Now, the method is really, it's full of a fairly simple intuition. It's to say that if I had two different sequences of paths, and if they share the same conditional future behavior, so if their future conditioned with the past with x1 or x2 was statistically identical, then we reason we don't need to remember any information that distinguishes between these two paths, because any such information is irrelevant for future prediction. So that allows us to sort of take the set of all paths and divide it into equivalence classes, such as two paths lie in the same equivalence class if they have the same conditional future behavior. And this allows us to, instead of storing the whole path, simply store which equivalence class a particular path belongs to. So we can collapse the entire dynamics of the stochastic process into a physical system with sort of the same number of distinguishable configurations as their equivalence classes in some one-to-one mapping. And one can show that once we have this, the entire dynamics of the stochastic process can be written as a standard stochastic map on these causal states. In that once we see a particular past, we can set up our system to be in the right causal state corresponding to that past. And then we can sort of construct a systematic stochastic map which, interacting with a blank tape at each time step, generates the right output. So in this way, we can sort of build a system that autonomously evolves, giving the right output as long as we feed in the right initial conditions. And this gives us this notion of a causal or predictive model. And it turns out to be a very concise description of how the stochastic process can be sequentially generated using sort of the same dynamics at each time step. The only memory here that's been carried between one time step to another is through this wire up here. And that simply contains the causal states of the machine. So that you can think of as information that such a model propagates from each time step to the next time step to be able to replicate its future behavior. So you can think about this information or these stochastic processes kind of like a river. They're propagating information from the past towards the future. And at every time step, that information has to travel somewhere to establish those correlations. And in this model, this is sort of that river. This is where the information from the past is being propagated to the future at each individual time step. And when we start characterizing the memory that's needed there, the one way to do that is through the entropic notion. And that's fairly simple, as simply the Shannon entropy of the causal state distribution, which just tells you on average, if you were to sort of simulate many copies of these processes, on average how much information is needed per copy. And it's given by this entropic measure here, where pi is just a probability of being in a particular causal state Si. And this object here, let's see what it means for these random processes. So if we take a look at our sequence of random coin tosses again, we see that here we have a completely random sequence. So every past has the same conditional future, because the future doesn't depend on the past. If we're throwing random coins at the beginning, we're going to end up with random coins in the future. So every past belongs to the same causal state. So there's only one state in the machine. The entropy of that is 0. So this corresponds to our natural intuition that if I was generating a sequence of coin tosses, I don't need to sort of remember anything. I can close my eyes and I can throw coins. I don't need to remember anything about what I have sent out before. There's no need to remember anything about past behavior. And so the amount of memory that's needed to generate the future, in this case, is 0. And so a guy by the name of Pratt Field in 1989 was able to show that this way of building these models were provably optimal. That once you sort of divide this into causal states, that's it. There's no more information we can discard. So he showed that these machines, which he called epsilon machines, are the optimal machines in terms of the memory they needed. And in that sense, he sort of motivated this quantity C mu, so the entropy over these causal states, as a fundamental measure of structure and complexity of a stochastic process. So he said, look, since there's no machine that can use less past information to replicate future behavior, this really captures how much information has to be propagated from the past to the future to see what we have observed. So this means that if we sort of take a human brain and we sort of take a neuron, we measure we get a sequence of data. Then from that sequence, we can't say too much, but we can say, okay, at least it needed to have this much structure to be able to generate it. It's probably like people did this experiment, it's like 7 bits. So we know our brain probably has a lot more than 7 bits of data. So okay, but at least it's a lower bound, right? So this is a basic idea of how these things work. Now, I should mention that, of course, this has since then been adapted into a wide range of different phenomena. If you search statistical complexity, random complex system, you'll probably come up with a paper about it. So people have looked at economic collapses, propagation of neural networks, atmospherics, etc. recently there's a paper about Bitcoins in them as well. But there's a paper about Bitcoins in anything, right, at the moment. So now what we have is that despite all this study, one of the particularly interesting phenomena people found was that these machines were still wasteful. They were still a causal waste. So what do I mean by that? Well, the way to think about it is through the notion of information theory. So here we have the amount of information contained in the past. And here we have the amount of information contained in the future. Now, in the middle here, this mutual information just captures the shared information past and future. So it's the amount of extra knowledge I can gain about my future statistics if I knew everything about the past versus if I knew nothing about the past. And it forms a fundamental lower bound in how much information we have to communicate from the past to the future. Because if we could communicate less, then we can break the second law of thermodynamics, Haléville's bound, information processing equality, lots of stuff. So we need to at least be able to store this much information. But at first, there doesn't seem to be any a priori reason why we can't just store this information. Turns out, though, that when people looked at these epsilon machines, in general, for general stochastic processes, they need to store fundamentally more information than the mutual information between past and future. So they had to store some extra data about the past. And we can see that if we were to run this model, and if we were to execute it and generate all the future statistics, then during that process, at some time during this process, information about the past here is being erased because it's never reflected in future statistics. So these models, in a sense, are fundamentally irreversible. They're erasing some information about the past that they needed to begin with to be able to generate the right future predictions. So there's some element of enforced or unavoidable irreversibility or irreversible waste in these models. And this was sort of quite a puzzle. It was first highlighted by this paper, which we'll come back to later, titled The Barbed Arrow of Time. Quite a catchy name, which got them a PRL, naturally. So what our first contribution was to look at this, and we thought, well, okay, here's a classical thing. Perhaps we can do better quantum mechanically. The story really goes that one of the mathematicians from Bristol by the name of Caroline Weisner came to Singapore around about 8 years ago to CQT. She was here just to go diving because she thought Malaysia and Thailand was great diving spots. But then she thought, hey, Singapore is a good place to sort of drop off and have chat about science before she went off diving. And CQT happened to be the closest to what she was doing. I mean, she couldn't find anyone doing the information theory stuff she wanted, but here were people doing quantum information, so she joined us. We had a chat. She said, look, this is an interesting thing going on. And we thought maybe we can do something out of it. And it eventually came out to be this paper here. And she had a very great dive as well. So the way that these models work is that what we were able to show was that whenever you had that waste, whenever the optimal classical model was still storing unneeded information, we could build a quantum model that was able to generate the exact same future statistics, but while storing less information from the past. So we could do this more efficiently. And this was basically true for any generic process where there is waste. So let me sort of illustrate how this works with a fairly simple example. So here is the case of a coin. So imagine that you have a box, and inside the box is a single coin. Now at every time step, what we're going to do is we're going to shake the box so that the coin inside flips with some probability Q. And this is going to generate a sequence of data, zeros and ones, where sort of consecutive numbers of ones and zeros occur with a probability proportional to 1 minus q to the power that they've occurred. So it generates these statistics, and here's a laboratory demonstration of this. This was done by my faithful postdoc and PhD student here at CQT earlier today. So this is right out of our theory lab. So if you're wondering what sort of labs we have on the 6th floor in CQT, this is the sort of labs we have. We do really advanced science over there. But you can see that they even got the slow motion camera going on. So this is quite cool. So demonstrates sort of this perturbation. There it goes fast again. Anyway, so we do this, we collect the data, and we end up with the sequence. And the question is, it's a Singapore coin. This is a local experiment. This was not done elsewhere. Didn't outsource this at all. This was done by local students. like, I don't know, maybe half an hour. I'll have to ask them about the amount of time. But it looked like hard work throwing this coin around. So anyway, if you do an undergraduate project with me, maybe you get to do this. And maybe something more exciting as well. Okay, so what we end up is we get the sequence of statistics. And the question is, okay, let's look at the optimal classical model to do this. Well, if we think about it, this is a Markovian process. At every time step, it only depends on the state of the coin at the previous time step. So the only thing relevant about the past was whether the last observation was 1 or 0, whether the last coin toss was heads or tails. So we can divide the set of all past into two separate causal states. Now, the future does depend on whether the coin is in heads or tails, so you can't discard any further information. And when we look at it, since both of them occur with equal probability, the amount of memory that's required is 1. So it requires 1 bit of entropy. And this is true as long as Q isn't exactly 0.5, where it is completely random. Now, one of the interesting things here, though, is that as we shake this box harder and harder, the coin is going to flip. So as Q goes towards 0.5, the process is going to look progressively more and more random. So there's going to be less common. The shared information between the past and future is going to gradually diminish. And so that means that the past is containing progressively less and less information about the future. And yet these classical models turns out to still need to store one coin. The state of the coin. So they should. So here we can see that there's some sort of waste involved, and this is where quantum mechanics comes in, because what happens is classically, when we look at the future sequence of data, 0, 1, 1, 1, 0, we still don't know whether our model was initialized in heads or tails. So some of that information is used to store whether the model was initially in heads or tails has gone to waste. But quantum mechanically, we have the freedom to write something down or not write something down at the same time. So that's exactly what we're going to do. We're going to do a superposition of these at the same time. And what we're going to do is we're going to store the state of heads and tails in two separate quantum states on a qubit. So exact forms here doesn't really matter, but you can see that it does depend on the probability value Q. The only thing that I want to point out is that because these two states are not mutually orthogonal, the amount of entropy used to distinguish them or store them is reduced. And as we tend Q go towards 0.5, the two states become closer and closer together. And therefore, the amount of memory that's required to distinguish them is also reduced. And so once we do this, the next step of us is we have to make sure we can still generate the right future statistics. And it turns out that after some thinking, one can come up with a nice quantum circuit that allows us to replicate the exact same statistics, but instead of a classical stochastic process at each time step, now we have a unitary quantum circuit. Once we read out the past, we can encode it in the correct quantum state, and then this machine can just go ahead and generate the right conditional futures each time step as long as we feed in a blank tape. Each of these things, you can also think about them as POVM. They're just basically of a quantum system. You're interacting it with the environment. You're measuring that environment in some appropriate basis at each time step. Another way of thinking about it is purely from the open systems model. So what happens is that the entire dynamics of the stochastic process can be thought of as a quantum system and a unitary evolution with that at each time step interacts with a probe, which is then measured in some particular basis. And the memory that's required, characterized by the entropy of this quantum system, can be reduced compared to its classical counterpart. And it turns out that, in fact, for every stochastic process, we can build these unitary quantum models. So if you're interested in the exact construction, that's in this paper down here. So we got some people to do some of the first experiments on this. So this was a group in Australia led by Howard Wiseman and Jeff Price. So they implemented some of the first experiments testing exactly this model. So they were able to simulate a coin being thrown in a box. Not that impressive, but they managed to do it using single photons, tested and they were able to show that what happens is that the entropy of the memory that they retain per time step is reduced over its classical counterparts. And you can see that classically, we always require entropy of 1 because we need to store that state of the coin. But quantum mechanically, the amount of memory that we need can dip all the way towards 0 as Q approaches 0.5. Of course, this is just a fairly simple example, but it sort of illustrated that, that our notions of complexity may change depending on whether we're able to use classical quantum information. People were able, previously in literature, CMU, the statistical complexity, was considered a very much an intrinsic property of the process that characterizes structure. But these results show that it's only intrinsic if we were to use classical information to model it. But if we assume that we could use quantum models to model the same process, then we might get different behaviors in complexity. So much of our recent work has been looking at just how these properties change. For example, one of the things is, do they have different qualitative behaviors, not just quantitative behaviors? And can we study some more complex, more physically motivated systems? One of the first systems we looked at was still a fairly simple example. It was one of the first examples to be analyzed in classical complexity science, and it's just a classical Ising spin chain. And what we've shown was that indeed we had these different qualitative behaviors. As we pumped up the temperature, the amount of information needed to model it in terms of if you were a man that's traversing the spin system from left to right, and you want to predict what you're going to see in the future, depending on what you've seen in the past, the amount of memory needed by a classical person would scale with the temperature. It would grow monotonically with the temperature. But quantum mechanically, it rises to some maximum before falling down monotonically as we further increase the temperature. This was picked up by the complexity theorists who got excited by the prospects of what they termed the ambiguity of simplicity, which is that they often had this belief that there's this totalistic hierarchy to complex systems, or at least some semi-directed system, where partially directed system, where if A is more complex than B, then that is sort of a very intrinsic absolute thing. But what they were very fascinated by sort of these results was that this notion of complexity can be different depending on whether you had classical quantum systems. So the two systems, A and B, can look more A could look sort of more complex than B classically, but B could look more complex than A quantum mechanically. And this is something that currently the group in Australia is sort of doing experimental demonstration as well on the archives. The next thing we were interested in is, of course, scaling, because if we were thinking about this as a practical application for actually simulating complex processes, then a constant factor isn't that important. What's really exciting is if we can get some sort of scaling. And indeed, we were able to find a number of families of processes where we do get a scaling difference. So we can get scenarios where the quantum memory, as we sort of scale the complexity of the system, essentially is capped by a constant number, but the classical memory grows monotonically. One of the first ones that we looked at this was sort of random walks on a circular ring, but we'll see a few other examples a bit in a few future slides. Another example is in terms of continuous modeling. This was done primarily by my research fellow Tom in the audience there, and that's basically generalizing these ideas of stochastic processes beyond just discrete time steps. We start looking at continuous time processes. So this corresponds to sort of more natural systems where an event could happen at any particular point in time. And then what you end up is your stochastic processes get generalized into these spatial temporal processes where you also have a time component and a distribution in which events happen. And again, what we end up is we find certain processes where we end up with a scaling advantage. Then so what happens here is that as we sort of take this process and we try to track it to finer and finer time scales, classically we need to sort of remember this time to finer and finer time scales, and that requires progressively more memory. But quantum mechanically, what we end up with is that for certain processes, we end up with this bounded scaling. So we're able to sort of simulate certain processes to arbitrary precision in time using finite resources. And this was recently in this article in NPJ Quantum Information. We also looked at sort of another area that's kind of exciting for us is to look at adaptive processes. So once you start thinking about agency, so agents, they're not passive objects. They don't just look at data in the environment. They also want to change that data. A stock market, for example, you want to look at the stock and you want to choose to buy or sell, and that could affect the stock prices later on. So once we look at more complex systems, we want them to be interacting, and we want there to be sort of this feedback. And so you can generalize this notion of computational mechanics to these input-output processes as basically how much information an agent needs to store about the past to be able to make the statistically correct decisions in the future. And once again, we get sort of this sort of memory advantage. And this actually turns out to be a particularly interesting one, because what happens is that you can think about these processes at each time step as having a particular input, xt, where it outputs a particular output, yt. And this we can map into a system where we undergo some sort of quantum interaction with a probe, where the input at each time step is just the different choice of bases in terms of measurement. And if we look at this system, for those of you familiar with contextuality, then many of the contextuality inequalities are really about taking a quantum system and measuring it in different bases at different time steps. And so you can use the same formalisms to start understanding things sort of to start characterizing how much memory has to be propagated in sort of these contextual inequalities. So you imagine you have a quantum system and displays some sort of contextuality inequality when you measure it sequentially in many time steps. And we know that the way that we can always replicate such a system with a classical process if we were given sufficient memory. Because if we had a quantum system where we had a black box, it looked like it was exhibiting a contextuality inequality, we can always lock a PhD student inside, have them compute the laws of quantum mechanics, and output the right outputs. So in this way, we can start looking at the memory costs of contextuality inequalities. And so this sort of leads to sort of the final topic that I want to quickly mention is that so there's all this excitement about changing the notion of complexity, but actually this interface also helps us give a new perspective to some of the interesting questions in quantum information science as well. And the particular one I want to focus on is the idea of the arrow of time. So this actually originated from a nice piece of work in the computational mechanics literature, where they were looking at this asymmetry between prediction and retrodiction. So what they were looking at was they were looking at a stochastic process, but they looked at sort of the amount of resources needed to model it in one temporal direction, so from left to right, versus from right to left. And what they found was that there was in general a resource difference. That when we took a stochastic sequence of data, predicting what's going to happen in the future may fundamentally cost different amount of resources from retrodicting what will happen in the past. And another way of thinking about this is that if we were to build a model of this process going forward in time versus the model going backwards in time, one of those models will necessarily need to be more complex than the other. And this was sort of highlighted back in that paper, Times Barbed Arrow, and this is why they called it Times Barbed Arrow, because what they hinted at this paper was that this was a very interesting way of getting an asymmetry in time purely from observational statistics, because this is one of those arrows of time that we don't need any external postulates for. All we need is a sequence of stochastic data. So we imagine that we got a bunch of data, and we're tasked with sort of with two different postulates. One is the data. There was a system that output data from left to right. The other is that the data was caused in the reverse causal direction. That the data was sort of generated from right to left. And the question is to make a decision, an educated guess, whether this data was generated from left to right or from right to left. Of course, in principle, it can be generated in both ways. But what they were able to show was that in one causal direction, generating the data would cost more resource than in other. And if this resource grew was substantial, then perhaps there would be a natural tendency to generate this data in one direction over another. And analogy that was mentioned was this idea of movie frames. It's kind of like you're watching a movie, but instead of the movie being played out to you, you're just giving frames of the movie in different sequences in time. And you're asked, would this movie make more sense played from left to right or from right to left? And it's in principle, you are able to build a model of the events occurring in both sides. But But in one causal direction, things might just look a little more natural than the other causal direction. And this was the idea that they wanted to capture in the asymmetry between prediction and retrodiction. Of course, everything done was classical. So what we were naturally interested in is what happens if we talked about things at the fundamental quantum level? Because after all, we tend to think about the universe, at least here we think about the universe, as being just natural unitary evolution. So at the underlying level, there shouldn't be this sort of asymmetry. So where does this asymmetry arise? And so here I want to briefly introduce this, another notion. So what happened was when the computation mechanics, they looked at this phenomena, they characterized it by statistical complexity. They weren't quite satisfied. They also characterized it by what's called the max entropy, or basically the maximum number of causal states that they need to generate, or the dimensions of the configuration space. So according to both of these measures, it turned out that there's a symmetry between prediction and retrodiction. This is statistical complexity that I've introduced. This is something that's not used as much, but still used in the complexity community. It's called topological state complexity, and it captures the minimum number of configurations that we need to be able to generate the right future statistics. So let me do a quick illustration of where this asymmetry comes from, because it seems quite magical at the moment. So what we're going to do is we're going to return to this perturbed coin. Everything here looks, so this was the same system as before. We're just throwing this coin at different, at each time step. And we can see that this process here is statistically symmetric. When we reverse time, then the statistics look exactly the same. And indeed, we can use the exact same process to generate this data forwards in time or backwards in time. So this is one of those processes with no causal asymmetry. It looks the same both ways. There's no natural preferred causal order. And the way that we can introduce asymmetry is to post-process this process. Imagine that we take the output data. And what we do is that whenever we see a consecutive sequence of zeros, we're going to take the first zero and we're going to replace it with a 2. And we're going to scan across this, and we can see another, wherever we have a consecutive series of zeros, here's a single zero replaced with 2, here's a 0 we replace with a 2. So once we do this, we can actually naturally induce asymmetry. And the way to see this is that if we were to do this process from left to right, there's a very systematic way of doing this. We scan 0, 1. Okay, 1 turns to a 0. This is the first 0, so we should change it to 2. 0, 0, 0, unchanged. 1, 1, 1. This is another 0, we should change it to 2. So as we scan it from left to right, there's a very easy machine that does this. But if we want to try to do this from right to left, things get significantly more complex. Because if we're scanning this from right to left, we have 1, 0, 0. We wouldn't know whether we should change this to a 2 until we scan forward in time and saw that 1. So you can see that by this post-processing is easier to do in one direction than another. And indeed, once we start building the best optimal causal models for this, they look quite different in the forward and reverse directions. In the forward direction, the model looks very similar to the standard model. We still just have the 2 states, except that each time now, whenever we flip the coin from heads to tails, instead of recording 0, we record a 2. That's the only difference. The memory overhead, there is no memory overhead. We can still use the same system to generate the right data. However, if we were to do the reverse direction, the actual model, it's a bit harder to see this. So in the interest of time, I won't go through the details, but essentially one has to remember significantly more information. We end up with a system with 3 states as the best way of generating that data in reverse time. So we end up with this asymmetry. And when we start looking at the memory costs, indeed they differ. In forward time, we just have that state of a single coin. That's one bit of information. But in reverse time, depending on the probability of perturbation, we can get significantly more memory. So we started looking at this quantum mechanically. We want to see, okay, quantum mechanically, do we still get this difference? And to be honest, when we started this project, our suspicion was that we would still see this difference. And for us, that would have been very exciting. It meant that we have reversible quantum behavior, and nevertheless, we still have an emergent arrow of time, which would sound very, it would be a very interesting result. But what we found was actually surprised us even further, which is that when we started looking at the quantum models, At first, it looked like they were quite different. So the predictive model looked like this. We had a system that looked very much like one of the circuits that I drew before. And the retrodictive model, we needed 3 quantum causal states. They were the exact forms, doesn't really matter too much, but they're outlined there. We have a more complex circuit. It required more gates. Things looked like, again, that it was going to be harder to generate in forward versus reverse time. And I guess in terms of number of gates used, that is indeed true. But if we look at the amount of information needed, it turned out that that when we looked at the quantum states that we needed, both the forward and the reverse models collapsed into a single qubit. So here's the forward model, here's the reverse model. Despite the fact that we have 3 separate states, they all still can be encoded in the same 2-level quantum system. And so the first thing that we noted was that the dimensions needed to generate the forward and reverse time quantum mechanically was the same, whereas classically they were not. And when we looked at the memory that's required, it turned out to be exactly the same as well. The quantum memory needed for the optimal causal and retrocausal model was exactly identical. So what this showed was this idea that causal asymmetry can vanish in the quantum regime, that we can have a process where there's this distinct preference of generating this data in forward versus reverse time classically that is not present quantum mechanically. So this notion that this natural notion of causality that we see when we observe an object could be a function or induced by sort of enforcing a classical causal explanation. That if we went to a quantum causal explanation, this asymmetry can entirely vanish. And so what we were interested in was to look at more general processes. So we studied very general stochastic processes where we basically had some sort of notion of causal asymmetry. So it took a certain amount of resources for prediction, a certain amount of resources for retrodiction, and this asymmetry here measured this overhead, this causal overhead of sort of modeling it in the wrong temporal direction. And what we were able to show was that we could build a quantum model that was provably better than the optimal classical model in the sort of the best possible direction. And whenever we can build a model like that, we can also build a model running in the reverse direction of equal resource cost. So what this meant was that this overhead here can be entirely mitigated by the use of sort of quantum models. And so we can derive a general theorem that says that the amount of memory that's needed to model something quantum mechanically in either forward or reverse time is always less than the optimal direction of modeling it. So in the sense that if we are forced to model something in forward time quantum mechanically, we can guarantee that our model will use less resources, not only than the best classical forward model, but also the best classical time reversed model as well. And so what this implied was that this classical overhead, or this classical sort of asymmetry between prediction and retrodiction can be entirely removed when we go into the quantum regime. And indeed, it actually holds both for the entropic notions and for the dimensional notions. And this is, if you're interested in the details, this is currently an archive paper, which should appear on Physics Review X, I think scheduled for the 9th of July. So keep an eye out for that. I should mention that these things actually, sort of, one of the interests was obviously the foundational consequences, but it also had an interesting practical side consequence as well. Because you can get these classical processes where this causal asymmetry can become unbounded, in the sense that it takes a fixed amount of memory to generate the data in one direction, but if we wanted to generate the data in the time reverse direction, the amount of memory needed can scale with the size of the system. So whenever we have systems like these, what we end up with is a natural case where we can get the scaling advantage between classical and quantum models. Something that can take many, that might require an unbounded number of classical bits to simulate, may require quantum bits in a bounded dimension and a bounded entropic memory. And so I guess sort of as a quick summary, the take-home message here is that I guess the main take-home message is that there's these two fields, quantum sort of quantum information, complexity science. And in fact, there's a lot of interesting overlaps between them. What I've talked about here is really just one such case. We looked at this fairly prominent notion of complexity, this notion of statistical complexity in the complexity sciences, and we took the concepts from classical information theory and looked at how they behave differently in the quantum sciences, and it turns out to have remarkably rich behavior. And I think that this sort of intersection between this quantum and complexity science has a lot of interesting possibilities yet. So some of the things that we're looking at, for example, is thermodynamic consequences. So we're looking at sort of, can these notions of complexity and the difference between classical and quantum regimes actually have thermodynamic benefits in addition to memory benefits. So one of the things that we recently studied was the idea of the amount of thermal resources needed to generate certain patterns. As we know in thermodynamics, if something is in statistical equilibrium, then it has no free energy. And as long as it's not in statistical equilibrium, then there is some sort of free energy. Usually when we think about standard thermal physics, that non-statistical equilibrium is having a hot reservoir and a cold reservoir. But it doesn't necessarily have to be that. It could be that you have something with a certain pattern in it. So if you had a pattern, that wouldn't be at statistical equilibrium. So one of the interesting things that's been studied in the complexity community today is about the thermodynamics of patterns. So they're interested in reservoirs or pattern reservoirs where you have certain periodic or certain complex behavior, and the question is, can we take that pattern and extract energy from it? And how much memory do we need to do that? And one of the things that's needed, of course, is that if you want to extract the free energy from a pattern, you need to be able to predict what's going to happen next. And that's where these predictive models come in. So you can build pattern energies that basically take raw data that is completely a default tape that's at statistical equilibrium to create some pattern by generating, using energy, and then doing work by sort of extracting that pattern to do work, forming sort of a pattern engine. And the efficiency of these pattern engines turns out to depend fundamentally on how much memory that the model is using to track that pattern. And so what we're interested in here is whether or not quantum mechanics allows more efficient ways of harnessing non-equilibrium resources. And this could have sort of interesting effects in terms of complex adaptive systems. Biological systems may not be quantum, but if they were quantum, they might be more energy efficient. So this is one of the directions that we're working at the moment. Another is, of course, looking at the applications of these quantum models beyond just reduced memory. One of the things that is interesting to note is that so far with all these models, what we've been thinking about was just generating the right statistical data. So we've been just throwing out the qubits in the tape and measuring them in a standard basis. But if you don't measure that tape, what it generates is actually what's called a quantum sample of the stochastic process, a superposition of all possible conditional futures. So before we collapse a wave function, it's actually a quantum superposition of each future possibility weighted by their probability of occurrence. And in many cases in previous literature, quantum samples are known to be more powerful than their classical counterparts. For example, if we could build a quantum sample of the isomorphisms of a graph, so we can efficiently solve the graph isomorphism problem. So perhaps there are computational advantages in just taking these superpositions of conditional futures, perhaps by interfering them to be able to find out something about the future that would otherwise be computationally intensive to calculate. So that would be an interesting direction that would love to discuss with anyone who has some ideas on. And of course, if we look at these systems here that's been generated, they're actually a many-body system. It's really just a complex spin chain. So this led us to this connection between possibly MPS states that's used to describe these spin chains in many-body physics, and see if they can be used in causal modeling. So bring some of the tools from MPS states to sort of the modeling and prediction of complex stochastic processes. And it turns out that there's quite nice analogies. You can take an epsilon machine, build an MPS out of it. The complexity of the machine turns out to be equivalent to the bipartite entanglement between these spin chains. So there's some interesting mathematical results that we're still trying to get our heads around to see sort of how we can use them to sort of say something interesting either about many-body physics or about sort of complex systems. So these are ultimately, of course, what we're funded on by the NI Fellowship is to also take these things and to look at to apply them to real data, to see if many of the existing studies of complex systems can change once we sort of go from classical to quantum simulators. I should mention that the complexity theory community is getting quite interested in these results as well. So we started, this really caught on among the complexity scientists probably around about 2015. And sort of we were invited to start running this sequence of satellite workshops as part of CCS, which is the largest conference in complex systems that happens each year. So the first one was held in 2016. This was one of my colleagues of LATCO. He was giving this talk at the Church of Higher Hilbert Space, as he'd like to call it. You can't really see the title, but the title is What is a Qubit? So it's a fairly rudimentary, but a lot of the complexity theorists got very excited about these qubits. So this has been running as an annual satellite workshop each year. This year it will be held in Saloniki, Greece. Actually, submission deadlines is still 4 days away. So if you got some research that bridges quantum and complex systems, give the website a look. We'd love to have you in Saloniki. I haven't been there, but it looks quite fun. So it should be a good place for a nice party. I'm also told that Oktoberfest is right afterwards. So that's a good excuse as well. So here's a group that's been working with me on a lot of these projects. So we have about 4 postdocs with 5 PhD students, and sort of they're roughly distributed at Complexity and here at the Center for Quantum Technologies. Many of them are in the audience, so feel free to have a chat with them. And here is a sequence of papers if you're interested in some further reading. I couldn't fit them all in one page, so these are the primary ones. And these are a lot of the people that are involved in the project, mainly from CQT and NTU, but we also have some collaborators from Griffith University as well. Great. And I think that's it. Thank you very much, guys.